So we've all heard about memory leaks, but what's leaking, where is it leaking to, and why does it matter? If we think about the programs that we write, then you probably know that it uses up RAM. First, when the operating system loads our program, it's going to put all of the actual binary executable code into the text segment. Now, this shouldn't change over the course of the program, so this doesn't really have the potential to leak. Then the instruction of your program is going to put your constant variables and static stuff into the data segment. And again, you might change the values in here, but you're not going to change the allocation amount. It's going to stay within its box. So there isn't much of a memory leak possibility there. Going over to the stack is dynamic. You can add to it, remove from it, and we could indeed have a memory leak here. For example, endless recursion calls or something like that. But there's safeties built in on both sides of the stack to keep it locked in. As soon as we overflow, the operating system is going to tell our program that we've had an exception or a segmentation fault or something like that. And it's probably going to give us a momentary chance to fix it. And if not, then our program will be killed by the operating system. So this doesn't really count as the traditional memory leak that can sort of run away from us. Now, looking at the heap, of course, whenever our program needs more RAM during runtime, for example, to create new objects or allocate space for buffers, we ask the OS to lend us more RAM, and it goes in here in the heap. The operating system expects us to give that back when we're done with it. So programs work in a sort of equilibrium with the operating system. We get RAM, we give it back. We get more RAM, we give it back. So everyone is sort of happy here. That is, of course, until we stop giving the memory back. And this is when we have a memory leak. So what happens in this situation? If we continue to allocate from the operating system and we don't give it back, then we're just going to consume more and more and more and more RAM. And the operating system is going to continue to give it to us. And even though it looks like our initial heap is this size, what's going to happen is when we fill that up, the operating system is actually just going to give us more and more space. In reality, the operating system is going to give us all the RAM it possibly has until we've taken up virtually all the physical RAM. And at that point, he's not done giving us RAM. When physical RAM is filled up, the operating system is going to look at RAM in general for all the processes that are going on, and it's going to see which pages of memory are not being used so much. And what it's going to do is it's actually going to swap those pages of memory onto the physical disk that you have. So whether it's your solid state drive or your hard drive or whatever it is, freeing up space in the RAM so that you can continue to allocate. So not only did he give you all the space he had, he's actually going to take RAM from other programs to give to yours. He's going to look for the least frequently accessed pages of memory to put it onto the disk. And as you continue to allocate, causing the swap space to be filled up, other programs now start to slow way down, because since a disk is so much slower than the RAM, and the programs need their data to be in the RAM to use it, the operating system and the CPU is going to find itself waiting for these data transfers to occur more than it's actually running your programs, because the disk is so much slower than the RAM. So we have this juggling effect here where program needs data, but it's on the swap space, so it swaps. And then that program can work. Then another program comes and there's another one here, and they have to swap it back into RAM and swap these out and execute. And we can see how this just becomes a total lockdown on the system. And this is called thrashing. This is when the system shuts way down, everything gets super slow. And if you're on a system like Linux, they call in a secret super assassin called the killer, the out of memory killer. And what he's going to do is he's going to line up all the programs and he's going to see which ones are the baddest. There's like a bad rating. Now, your program, of course, if you line them all up and you can see this guy got all the memory and hasn't given it back, he may actually not kill this one first if you're using it, because he's going to have a really high priority. So your program, even though you've taken all the RAM and you've caused its entire mayhem, other programs might be killed first, sacrificed for your greatness. Now, of course, as you kill these programs, we have some space probably freed up in the swap space so we can restore some data and get some more RAM. So we have more space. So your heap is going to grow a little bit more now, but still, we're still allocating, right? So it fills it up anyway. The operating system has to kill some more processes until finally the OS just reaches a breaking point where it says, well, this program cannot continue to run. There's no more RAM left to give. I've given him everything in the world. And then ultimately, your program will be killed. There's a chance, of course, as we've all seen, that it's too late. The system recognized the danger way too late. The allocation is too fast. There's not enough time, not enough resources to handle it, and the entire system crashes. In modern times, that happens less and less. Usually you can get the program killed. But this is how a memory leak can destroy a system. And it's not as dangerous when we have a program that's run for a short period of time. But when you have a long running program, that's when it really adds up. And this isn't some like noob type mistake. Let's look at some impactful examples. And I'm going to start with an example out of this world, the Spirit rover. So the rover was on Mars, as we know, and it was 105 million miles away. And the rover, this little guy right here, he had flash memory where he'd store all sorts of like logs and data that he took, images, that kind of thing, before it could be sent to NASA. And of course, he had RAM for actual operations. And there was two problems with the rover. And together, it turned into the nastiest memory leak that I've ever heard of. The rover would store all the logs on its flash memory, but there was a problem. The rover wouldn't filter out any of the files and it wouldn't delete them, so it just kept on filling the flash until it was entirely taken up. That was the first problem. And then whether through some routine reboot or maintenance reboot or something, the rover rebooted, and this is when the real problem was revealed. There was a bug in the OS that it was running, where every time the rover booted, the RAM would mount the flash drive, and then it would look at all of the logs on the flash drive, and through this bug, it tried to pretty much open every single log, loading the metadata and the file descriptors and the tracking information, not the raw data, but the data that it needs to open the file. And this would fill up the RAM itself. So as soon as the rover boots, the RAM gets filled up by trying to mount the flash drive and look at every single log, causing the rover to reboot again and repeat the process. And this turned into a reboot cycle. Back on Earth, the NASA engineers were getting a signal every 18 seconds telling them that it was trying to boot, a major problem. So the engineers were able to identify that the RAM was filling up, and they were able to recreate the issue on Earth and figure out how to fix it. The only problem, of course, is right now, since the rover can't actually boot into its operating system, it can't really listen to commands. Fortunately, there is a bootloader on the system. The very first few lines of code that runs, and those are working well. So while normally the rover is listening for commands constantly from Earth, the bootloader had 1 to 2 seconds where it was listening to commands from Earth. So the NASA engineers knew that they had to hit a moving target 105 million miles away, 10 minutes in the future, because it takes 10 minutes for the signals to reach, with a 1 to 2 second window of opportunity to tell the rover to boot into safe mode and halt mounting the flash drive. It took them days to get this done, but they did it. And ultimately, it was about 2 weeks that it took from recognizing the problem to having the fix installed on the rover and bringing it back to life. An absolute amazing solution to do this across what I'll say that solar system. Now, if it were me, anytime I can't get into my BIOS, I start smashing the keys. So I don't know why they didn't just spam. I don't know why they didn't just spam the radio signal at the rover, but this is much more elegant and quite a beautiful solution. So absolutely incredible. The project for the rover cost about $1 billion, and it was scheduled to run for 90 days. So to lose 2 weeks of that 90 days costs about $100 million, a really big problem. Now, of course, the rover did go on to run for 6 years. NASA, in all its brilliance, adds so much redundancy to these missions that they're able to correct and fix these problems remotely. So absolutely incredible. And the JPL engineers that worked with this program ended up confirming that it was indeed an effective free command that was missing. So one line of code caused all this problem. So really, really incredible how memory leaks can affect something really tiny to something really, really big. Of course, operating systems have a lot of memory leaks. Mac OS X, I think Sierra is the most recent one that I'm aware of that had a pretty bad memory leak. Windows 10 had a bad memory leak with its File Explorer, where if you opened more File Explorer windows, there was like a pretty nasty memory leak. The video game World of Warcraft had a memory leak for an entire expansion, where as a player kept on crafting items over and over and over without closing the window, the game would be taking up 20 to 30 gigabytes of RAM, or I guess it's all relative. It depends on how much you have, but it will just consume all the RAM. But now let's create our own memory leak problems with some simple programs so we get a hands-on experience. So in C, we allocate from the operating system using the malloc command, and we give it back using the free command. Let's do a short sample. I'm going to define our buffer size, which is what we'll use to allocate, as maybe 16 KB so that it's very obvious when we allocate. We'll use a character pointer to capture the allocation each time. And then we're going to loop through 10 times, allocate our buffer size amount. And then I'm going to ask for a character input so we can control how fast it actually happens. Allocated. And now what we want to do is run it through our debugger, file grind. All right, so we have one allocation that goes through automatically. Then we're going to press enter. And each time we press enter, we're allocating 16 more KB from the heap. Debugger output a file here. You could see here that we are allocating onto the heap. And even though we're not keeping a reference to each of these blocks of data, we're using one pointer, right? And we're just reassigning the pointer to the new blocks that we allocate from the operating system. You can see they're not being given back. So even if we did want to free it, we don't really have any access to it anymore. This is a straight up memory leak. This is 16 KB every time. So by the end of it, we have 162 KB or so allocated. The problem here is that we don't keep the reference, right? Every time we allocate again, the previous allocation that we had on A is gone. So what we need to do is kind of adjust this a bit. So why don't we turn this into an array? Maybe we'll have 10 of them. We can have I just be our counter outside. And let's make it so that we have some actual commands that we could put in to allocate or deallocate, and just make it really simple. Use X to exit the loop, and we're gonna have some character returns. How about this? If we enter A for allocate, as long as there's allocations that can be made, let's check. So if I is already at the maximum, then we can just say that we're out of space. If we can allocate, increment I, allocate the buffer size. If C is free it, and we need to check if I is 0 as well. No more allocations. But if we can free it, free allocs, and we'll increment I before we allocate. And I think that should work. So A is for allocate, F is for free, and hopefully we can see the heap going up and down now. All right, that seems to work. If we put A, we should get an allocation. I didn't put a message. I should put a message when we allocate. If we go all the way up, it should give us an error message when we reach the max. So right now we have 10 allocations. And if we free all the way back down, then it should give us an error message when we reach 0. So let's leave it somewhere in the middle, and then let's press X to exit. And we should see it a lot more interesting now. Allocations coming on the heap, then we free some of them, we get more, and then we went to the maximum that we're allowing here, which is 10 allocations, which is 160K. Then we free all of them until we got the error message. And then we got some more allocations, and then we quit the program. So when we allocate 10 times, we have it stored in this allocs array. What if we cleared it? Let's try and clear it out afterwards. So maybe we'll have another command, D for dump. We'll go through each entry, and we're not going to free it. We're just going to set it to null. So if we allocate 4 of them, and then let's dump all of them. And let's allocate some more and dump, allocate some more. So we're able to dump and then allocate the full 10. Even though we're nullifying all of our references, the references that we forgot about are still there. And this is, of course, a straight up memory leak. So now we're actually at 500K. Just because we lose a reference to them doesn't mean that they go away. Let's do the same thing real quick in C++ and show that it's basically the same. And then we'll go to a higher level language with garbage collection, and we'll see the real benefit of garbage collection when we lose some of these references. What we're going to do now is, instead of just allocating the direct amount, we're going to have a class. Let's call it block. So we'll have an unsigned character, which is 1 byte, and we'll have 16,000 of them. Our array is going to be block now. And the actual allocation now is just going to be new block. And the free command now is going to be delete. Now we're using object-oriented programming, doing the same exact thing though, right? When we free, we're now using the delete keyword. And even though we're losing the references to the objects here, when we clear out the array, the object still exists on the heap. So the same exact thing as C. I'm back on Windows now. I'm using C#. Let's do the same thing that we did and see how the performance is different now that we have a garbage collector working. So I'm going to put the same block class in array. Each object instantiated will take up at least 16K here. I'm going to loop through 10 different times. We're going to add it to our list, and we're just going to have a new object like that added to it. Clear the list by going through each one. So I'm going to say press any key to clear the list. We can use something like blocks.clear. But instead, I think we should do the same thing we did with C++, where we actually nullify each one. We're just removing our reference, I equals null. So we'll launch our performance memory usage profiler thing. So we made 10 allocations here. Take a snapshot, and then let's proceed and clear it. We can take another snapshot. Could quit the program. When we took our snapshot after allocating 10 times, we have our 10 blocks. They're all roughly 16K in size. And then if we look at after we cleared the list, there's actually been a 160 roughly KB drop, which is of course the size of our data. If we search for block, there's nothing here. We nullified them. So if you remember in C++, when we nullified the array references, nothing happened. Data was still there. That's because we have to manually delete with C++. But in C# and Java and Python and languages that have garbage collection, it's basically keeping track of our objects. And anytime that we get rid of all the references, it will automatically clean it up and destroy that object. Now let's look at how a leak can actually happen with a garbage collection. I have a sample Unity project here. I think it's a lot more practical to see it in something like a game environment. I have a little icon here that I just made real quick. This is our little rocket, and I'm thinking that the rocket is going to appear to fly upwards. We're going to have to dodge obstacles, so really simple. Add an input handler. You can move left to right. A and D is what I'm choosing. Input handler script on move. It's going to pass us a vector2. Test it real quick to make sure everything is working. So we have left and right movement. You can see -1 and 1. I only want left and right movement here, I think. I'm going to make this a float x coordinates. So we have our x coordinate input movement controller. Take the input for an input. So we're just going to put transform.translate x axis times fixed delta time. Okay, so now we have some movement. We can adjust it to add a multiplier real quick. Multiplier. And we can add a range here. Okay, here's our slider. And as we move this up, we go faster and faster and faster and faster. And what if we max it out at 10? It's a little jaggedy, but I think it's fine for our little test. So now what we need to do is just have some objects falling down towards us that are spawning randomly, and that's where we'll have our memory leak. We can make it like a circle. Put an enemy controller, and what he's going to do, go down. And we'll put time speed, and we'll just put a float here. So he's just going to move downwards all the time. There he goes. We'll just randomize it a bit. Say 5 is the lowest, 7 should be the highest. So now what we need to do is get a spawner that will just start spawning these guys, an empty object spawner. And all he's going to do, spawn these items around here. Game object, call it prefab, respawn coroutine. And we'll just have like infinite loop here. Whatever the spawn time is, 0.5. I guess we'll have some setting is paused. If is paused, continue. And we'll make the pause mechanic be sort of like the culprit of our memory leak. So we're going to keep spawning unless we are paused, and we'll just put a spawn here, and up here we can have our spawn method. I guess on start, we should get the size of the screen, x minimum max, I guess. X min equals camera dot, I guess vector 3.0 to get the left side of the screen dot x, and then x max dot 1 dot x. So we're basically going to get the left side of the screen. This should be x max. All right, there's our minimum and maximum. So negative 12 and plus 12. On the start, we can just start our coroutine. And all we need to do now is instantiate, and then we'll just set the position, randomize it, x min, x max. Make this into a prefab now. That guy in here, so he knows what he's spawning. It's not randomizing very well, and our y-axis is not correct either. And yeah, I didn't even put a y here. Y val.viewport. Here they are falling down. It's not very random. It needs to be faster. So let's speed that up. 10 per second. So this is more like it. We can see here that if we pause this, of course, we have all these objects, right? And this is kind of a very basic memory leak, right? The objects just aren't being despawned. I would say severe negligence on the side of the programmer. So what we'll do is we'll just create a barrier so that when they hit it, they despawn. Like 50, and then our circle on trigger, enter 2D, destroy, collision. So we have these guys disappearing now. So we need to put this below us, of course, because it should be down to catch anything that falls like below the camera. We don't really die on trigger, enter. We'll disable our game object. So now let us add the real memory leak. What I want to do is add a pause mechanic. So I'm going to add an input here called pause. Do the letter P on pause. And then what we're going to do, fire off an event on pause, pass that in. So the event here on pause is going to be a Boolean. Oh, we already have on pause. Let's call it on player pause, I guess. Okay, so every time a pause update comes in to pause or to unpause, we're going to send an alert. What we want to happen here, or in this is a bad example, everybody, just to make sure we understand. What we might do here is when we start an enemy, right? When an enemy spawns, we might subscribe to input handler on player pause. We'll maybe have a function here on pause. So we're going to say on pause, and on pause is going to give us an error because we need to take in a Boolean here. Is pause. If is pause turn, and we'll just put is pause equals val. So we'll set the value of whether we're paused with whatever was sent by that update. So we press P and they pause. Now, of course, the spawner needs to listen to subscribe the spawner himself, void on pause, val is pause equals val. And then he's actually going to sign up input handler dot on pause, send it to our handler. Pause with P and unpause and pause. So now what we can do is we can look at our memory profiler. Tab it here at the bottom. And now let's run the program and see if we have a memory leak or not. We have all of these items. I'm going to take a snapshot. I don't know how many this is, but it must be about 30. So we have 31. Let's unpause it. So we can see it sort of maxes out around 30. There's only ever 30 at one time because we're destroying them as they go down. Let's take another snapshot and now let's analyze what's happening here. First snapshot, we had about 30 active units. So we should see about 30. So the first snapshot here, so if we look at the objects and we sort the type, and I think it's called enemy controller. So if we open this way up here, then we can see that there are indeed about 30 or so. We're going to see the count here. So there's 40, even though we counted 31. So that's kind of a bad sign, right? And in fact, we can see that these ones here, this is about the 31 here, and you can see there's some extra ones, and they have no name, but they're still on the heap. And if we click on it, then we can see that Unity itself says this Unity object is a leaked managed shell. It's taken up 48 bytes. They have no object with them. And this is, I think, a pretty common memory leak here. Now, we know that we're explicitly destroying the objects, right? When it gets to the end, right? We're destroying them. And we can see that the name of the object is gone. So Unity has indeed destroyed the stuff that Unity is in charge of. But when it comes to our objects and our scripts, that still needs to be collected by the garbage collector. And what's happening here is if we look at the second one, then we'll see the difference. So the first one, we let it run for about 30 to 40 objects. We don't really know how many were destroyed, but it seems that 1, 2, 3, 4, 5, 6, 7 had reached the end because those are the ones that have their objects like destroyed, the game object from Unity, but the script itself seems to still be alive. And if we look at this other one here, then we should see a much different story. Now, look at that. We have 176 here. And we know that we should only have 30 at a time. Look at how many don't have objects here. So what this means is that as these enemies are falling towards this bar, even though we're explicitly calling Unity to destroy them, which is a Unity feature, you don't have to worry about that too much. But what we're doing is we have no real references to it, right? The references are by Unity itself. So when we tell Unity to destroy an object, Unity is going to go ahead and destroy the references so that the garbage collector can collect them. And we see them all being deleted here. And we can see even in the hierarchy, the objects are being destroyed. They're vanishing from the game world, yet somehow, some way, they're staying alive in memory. And what I want to do real quick is show if we did have a real game going where it had maybe int like health, some random number here, string for like a special name, Fred, some kind of like log, an array of integers, right? 8 integers long. But the point is that it's going to take up a block of data. If this was at least a basic game that was playable. Before we saw it took about 48 bytes each. So now let's see how much space it's taking up, and then we'll find the source of the memory leak, although you could probably guess what it is. And in the beginning, we'll capture a new snapshot, and let's see how many enemies there are. None of them have reached the barrier yet, so none of them have been tried to be destroyed. We can see, well, let me actually make it so we can see. Our player died. But here they are all going into the barrier. I don't know how many have been destroyed so far, but it seems to be maybe 100 or so. So now let's pause this, capture a new snapshot. All right, so we have our second now, and let's analyze them and see what is going on. Let's count how many we have here at the end. We have 36. Okay, so if we go to our objects, this is right when the game started, right? So we can match it for enemy, and we should see that none of them are missing a name, right? So Unity still has their names and their game objects, and our scripts are alive, so there's no leaks here, right? Nothing had reached the barrier yet. This is what we took right at the beginning. And if we look at the second one, then we can see that there are a lot more than the 30. So we have about 31 or so, right? 36, I think, we counted at the time, of objects that are active on the scene. And look at how many have been destroyed, but they're not gone yet. A lot of it is gone. A lot of the stuff that Unity manages itself is gone. But the stuff that it depends on the garbage collector, right? The classic C#, Python, Java level stuff where the garbage collector is not. And we see now each of these scripts are 72 bytes. So a game like this, and we can actually see the breakdown here. We have our string here, the 8 bytes. This is proof, right, that the data is not gone. Now, if we randomize this data, we'd see different values, but all of them have the same value. And even their instance ID is still being buffered. So we can see the garbage collector is failing to collect them. And it's not because we're not calling the garbage collector or anything like that. We could try that and it wouldn't work. The main problem here is that in our programming, right, we were very sloppy. And by the way, in general, entire example is not very good because you might use an object pool for something like this, but that's beyond the scope of this video. But what we're doing with our enemies is as soon as they spawn, we are subscribing to an event, and the input handler is going to be telling it when we decide to pause the game. When Unity destroys these items, it's going to destroy the transform and a lot of these components, but the script still has a reference from this event, the on-player pause. And the key for a garbage collector is it's going to check if there are any references that exist. So in this case, our very innocuous pause mechanism that we made the enemy subscribe to is keeping them alive, at least this one script. So all the data in this script that's on the heap is being kept alive. So the way to combat this, of course, is we need to unsubscribe from the event to allow this script and this object to be reclaimed. So if we put something like on destroy and we put input handler dot on player pause and we remove ourselves, then this should fix the problem. You'd want something much more structured, but in this case, let's see if that works. So let's take a snapshot after some have been destroyed. We could just let it run for a while. We know that there's about 30 at any given time, right? We look at our objects and we filter the type by enemy. Then we can see here that all of the extra ones are gone. We have the same exact amount, probably, maybe give or take one for some sort of object-oriented like feature or whatever, but no extras without names, right? So in this case, the garbage collector has been able to reclaim the memory. We have no lingering references like we did before because we've unsubscribed them. And this is just one example of how easy it is for lingering references to kind of make its way into code with object-oriented programming where we're depending on the garbage collector. And it's a reminder that just because we have a garbage collector doesn't really give us like a blank check to do whatever we want. There's still going to be situations where memory leaks arise. So it's one of those things that we just need to combat against and use tools like debuggers and memory profilers and stuff like that to really find out where we have memory that's not being freed when it should be. So I hope this helps. I know it's a little bit of a complicated example, but I felt like a real life example in something like a small game can really be instructive. So I really hope this helps. Thanks for hanging out with me, and let's see what comes next.